Hello. Today's video will be about the role of the Wronskian matrix and, well, the determinant of the Wronskian matrix in determining what the linear independence or the linear dependence of solutions to differential equations. And here I'm hoping to go through some of the stuff that I won't be covering in class because it might be taking us too far afield. But for those who want to know what's going on behind the scenes, uh, this is for you. And we will be working primarily with two functions. So let's get started. All right. And let's remove this. All right, here we go, the Wronskian. Now, first of all, what is the Wronskian matrix? And I better make sure this is set up. Wronskian matrix, for example, if you have the functions y1, y2, y3, all the way to yn, well, technically the Wronskian will be the determinant of the following matrix of functions: y1, y2, y3, all the way to yn. Then you have the derivatives, y2 prime, y3 prime, all the way out to yn prime. And then going all the way down, let's say we go to the n minus first derivative. To the nth derivative. Sorry. So the first, second, and you're going to go up to the n minus first derivative. 1 and 2 and minus first derivative all the way down to here. And let's do an example so we know what we're talking about. So for example, let's do 3. Suppose y1 is x, y2 is e to the x, and y3 is, say, cosine of x. Then we get y1 prime is 1, y2 prime is e, that never changes, y3 is minus sine of x, y3 prime. Then y1 double prime is 0, y2 double prime is still e to the x, good old e to the x, and y3 double prime is minus cosine x. So the Wronskian and table W of y1, y2, y3 would be the determinant of this matrix. X, e to the x, cosine x, 1 e to the x minus sine x, and 0 e to the x minus cosine x. Now, if you're going to take the determinant, you can expand along any row or any column. This column has a 0 in it, so we'll just go ahead and take plus for this cofactor and minus for that one. So the determinant will equal, when you have this, it'll be x times the determinant of this matrix, e to the x by the sine x, e to the x minus cosine x, minus and minus is a plus 1 times the determinant of e to the x cosine x. You cancel this out, cancel that out, e to the x minus cosine x. And this would be x. Then we have e to the x minus cosine x. Minus a minus is a plus e to the x sine x. And then here we have a plus a to the x minus cosine x minus e to the x cosine x. And we can simplify if we wish. But I'm not going to waste my time just doing the arithmetic here, but you work this out, and yeah, you can, let's go ahead and do it. Let's factor out e to the x. Then we have a minus cosine x, so minus 2 cosine x, uh, minus x cosine x. Then we have a plus x sine x. So that would be the Wronskian for that, for those three functions. Now, what we're going to talk about in terms of the Wronskian is this. And let's just focus on two variables. On two functions. And what we're going to show is one, y1 and y2 are linearly independent. And we went over that in class. But roughly speaking, they're not multiples of each other, then they're linearly independent. If and only if the Wronskian of these two is identically 0, meaning 0 for all x. In other words, 0 is a function. And the second thing we're going to show is that if, conditioned on this, if y1 and y2 are solutions to a differential equation of the form plus a1 x y prime plus a2 x y equals 0. So in other words, if they're solutions to the same differential equation, then the Wronskian of these two is equal to 0 for all x, or the Wronskian is never 0 for any x. And so if you combine fact 1 and fact 2, the reason that's important, this is important because what these two things mean. So they mean the following. If y1 and y2 are solutions to this, this is a linear second order differential equation. If they're solutions to the same differential equation, then we can check, and if the Wronskian evaluated at any point whatsoever in the domain of validity, in other words, if this is not 0, then, for any chosen x naught, then the solutions are linearly independent. So in other words, this is for any choice of constant. And let me tell you why that is such a nice thing to have. So here's an idea. So suppose, for example, we have y1 is e to the 2x cosine of 3x, and y2 is e to the 2x sine of 3x. Now, the derivative of this one here, we got to use a product rule. So it's 2e to the 2x cosine 3x minus e to the 2x sine of 3x. And y2 prime is 2e to the 2x sine of 3x plus 3, and I realize I need a 3 here, e to the 2x cosine 3x. Now, if you probably put this, if you try to take the Wronskian, it's kind of a complicated, I wouldn't say it's complicated, but you have this, right? And then you have this here. And then we have this, and you were running out of room. We would see if this is 0. But as you can see, that's a kind of a messy thing, right? But with the second result saying that the Wronskian's either 0 for all x or 0 for no x, instead, why not do the Wronskian at a convenient point? And I want to choose 0 and check that out. So if I do that, that's the determinant. Now remember, e to the 0 is 1. Cosine of 0 is cosine of 0 is 1. Sine of 0 is 0, so that's a big fat 0. This is a cosine here. So this is going to be 2 plus 3 times 0. This is a 2 times 1 times 0 plus 3 times 1 times 1. And this determinant is a lot easier to check than this determinant. And that determinant is 3, and that's certainly not 0. So we can conclude by the second result that the Wronskian is never 0 for those two functions, which concludes that these two functions are linearly independent. So by this very simple calculation, y1 and y2 are linearly independent. So that's why this is such a nice result. You don't have to algebraically grit your teeth and grind through this and simplify. You can just plug in a number of choice. In this case, 0 works great. So that's why this is important. So let's go ahead and see why this is the case. So the first part is that we're going to show. For the first part 1, let's show that y1 and y2 are linearly independent if and only if the Wronskian is not 0. So let's start off. So 1, suppose y1 and y2 are linearly dependent. Now what that means from what we went over in class, this means that y2 is some multiple of y1. So if I calculate then the Wronskian of y1, y2, which is the determinant of y1, y2, y1 prime, y2 prime, which is y1, y2 prime minus y2, y1 prime. Well, we know that if you take the derivative of both, what this is going to equal, the derivative of a constant times a function is that constant times the derivative of that function. So this is going to be y1. y2 is just going to be the alpha y1 prime. y2, remember, is alpha y1 prime, and that's in fact 0. So if the functions are linear multiples of each other, the Wronskian is 0. That's kind of easy. Now let's go the other way. Suppose Wronskian is 0, identically. Now let g equal the function y1 over y2. And assume that y2 is not itself not 0. So now let's take the derivative. And by your good calculus students, you know that's the square of the bottom. Then it's going to be the top, derivative of the top times the bottom, minus the top times the derivative of the bottom. And you recognize what this is. Look at the top. The top looks just like the negative of the Wronskian. And it is. So the top is minus the, I'm not the derivative, it's minus the Wronskian. But if the Wronskian is 0, that's 0. So g prime is 0, which is which is a derivative of this. But this is 0 for on an interval of validity, identically 0. We learned in calculus that the functions that have 0 derivative on an interval are constant. So this means that y1 over y2, well, g equals y1 over y2 is a constant c, which means that y1 is c y2. So y1, y2 are linearly dependent. So now we figured out that the Wronskian can determine linear independence or not. Okay? So we'll go ahead and do this. Now, the next question is, now we want to show if y1, y2 are solutions, and object 2 or 2, the same differential equation, y1 double, now y double prime plus ax y prime plus b of x, y equals 0. So if these are two solutions to this differential equation, then the Wronskian is either never 0 or the Wronskian's always 0. So in other words, identically 0, never 0. So here's a little bit of preliminary information here. So the Wronskian, as you know, is going to be y1, y2 prime minus y2, y1 prime. Now let's take the derivative of the Wronskian just for the heck of it. And we're going to do something with this. Well, if you take the derivative of the Wronskian, you have y1, y2 double prime using the product rule. Then you have y1 prime, y2 prime. Now taking the derivative of this, and then also doing this times the derivative of that, you get this sort of weird looking thing here. And notice these two terms cancel. So the derivative of the Wronskian is y1, y2 double prime minus y2, y1 double prime. Now let's keep that in mind. So we know what the Wronskian is, and we know what the derivative is. Now let's assume that these are functions of they're both solutions to the differential equation. So you have y1 double prime plus a, and I'll suppress writing. Well, I'll write the x. You have that. But because they're both solutions, you have this as well. Now, what you do, because these are both solutions, you have that. Now, what I want to do is multiply this top equation by y2. And you still get 0. I want to multiply this equation by y1. Now subtract. And if you subtract, the b of x is gone. And what you end up with, if you subtract this, you have y1 double prime, y2 minus y2 double prime, y1. Let's gather these terms. Plus a of x. Then we have y1 prime, y2 minus y2 prime, y1. Now, let's take a look here. Look at the derivative of the Wronskian. That's y1, y2 double prime, right? So we have here, so y1, y2 double prime. And so this turns out to be minus the derivative of the Wronskian plus a of x. And look at what we have here. The Wronskian's y1, y2 prime. Let's see right here. y1. Let's see, did I do something wrong here? Yep, that's correct. So, yep, this is right. So, this thing, let me just do a double check. I'll make sure I got this right. y1 prime, y2 minus y2 prime, y1. That's correct. And let's see here. I want to make double. I have to triple check this. Okay, that's fine. So, all right, that's good. So this right here is minus w. And we have a 0 here. Okay? So multiplying by -1, we have y prime plus a of x. W equals 0. That's good. We've seen this differential equation before. This is linear first order. Therefore, if it's linear first order, its integrating factors we learned in class is e to the integral of e to the ax dx. So if you multiply both sides by the integrating factor, we get now the perfect product rule derivative. And then if we integrate both sides with respect to x, so now you tack on the integral of both x with respect to x. This is supposed to be an integral sign. What you get is you get this integrating factor, and that antiderivative is going to be a c. So the Wronskian is c e to the minus integral of ax dx. And this is e to the something. So this is equal to 0 only if c is 0, and that's true for all x. Otherwise, never 0. So the Wronskian's either always 0 or never 0, provided these are solutions to the same linear second order differential equation. So that's the whole thing about the Wronskian. So, and the way you might use that is, let's say let's say you found out, well, we already did a Wronskian there, but let's say you found out that we had the differential equation y double prime plus 25y is 0. And let's say you had y1 is cosine of 5x, y2 is sine of 5x. The Wronskian is going to be the determinant of y1, y2, y1 prime, y2 prime equals the determinant cosine 5x, sine 5x, minus 5 sine 5x, and 5 cosine 5x. Now let's use x as 0 because you can. Now it turns out this isn't that bad without that, but if you let x equal 0, this becomes a determinant of 1, 0, 0, 5. And by just checking the Wronskian at this one point, these functions y1, y2 are linearly independent. So thanks for watching. So we'll just stop this.